I'd like to welcome everyone to the Saturday Engineering for Everyone 2015 lecture series. I'm really pleased to see this turnout. My name is Scott Carney. I'd like to take a moment to introduce you to what we'll be doing this semester and to thank a few people, if you don't mind. So first of all, this is our schedule for the semester. I'm very excited about the list. I'll be giving the talk in 2 weeks. I figure I have to step up and eat my own cooking. And then after that, we will have my dear friend and colleague from physics who will come over and give a talk on quantum strangeness and various fun, exciting things you can do with light that probe the basic mysteries of the universe. We'll have my co-instructor and good friend Jonathan Makala talking about all kinds of things that are really related to space weather and how they relate to things that happen right here on the ground, earthquakes and tsunamis and the like. We have another good friend and colleague from physics, Laura Green, coming over to talk to us about superconductors. And since there's a certain energy theme going on, I think it's going to be fun and appropriate. Linford Goddard, another colleague of mine here in ECE, is going to talk to us about experimental design. And in some ways, it's going to be a talk about how we know the things we know and how you figure things out, and from a very basic perspective. I think this one's going to be really great for some of our younger members of the audience. And we'll wrap up the semester with one of our superstars, Brian Cunningham, who is turning cell phones into little laboratories for biomedicine. And one thing I'd like to point out is that running through 5 of the 7 talks, we have a photonics or optics theme. This was intentional this year. This is 2015 is the UNESCO designated International Year of Light. It's a very exciting time for people like me who have made their careers working with various forms of light. It is also, I think, broadly an exciting time in science. It's the sesquicentennial of the publication of the paper that really first explained that light is very closely related to electricity and magnetism. And so it's a great year. It's an exciting time. I think we've got an amazing slate of speakers, and I'd like to thank them first of all. More explicitly, I'd like to thank, of course, my co-organizer, Andy Singer. I think Andy's in the audience today. This is no small thing to pull together. I was very pleased to see Naresh Shanbag is here today. Naresh helped us organize last year. He's on sabbatical this year. We're going to rope him back in next year again. The ECE communications staff, I don't know how all of you found out about today's talk, but there's a good chance it was because of either Brad, Meg, or Nikki. Our friends over in physics who run the Saturday Physics for Everyone series have been incredibly supportive last year and this year in helping us organize this and make this happen. In particular, Inger Karliner, who I saw here today, has been an amazing resource for us, and thank you, Inga. My undergrad assistant, no, I did spell it correctly. I'm sorry. I blew it. But Sneha, if you're here, Sneha may actually be working out there right now, but Sneha's here. Thank you very much. She pulls a lot of this together. Our department gives us a tremendous amount of support and help. Our department head, Bill Sanders, is sitting right over here. Snacks are thanks to Bill and the department. And, of course, the overall support and use of the building comes from the Department of Electrical and Computer Engineering. I did actually blow Rick's name. Rick Langlois is, or I've been told I pronounced it incorrectly, but is here, or is helping with the recording today. This lecture will be recorded and made available on the internet, so if you think this was fun and you want to tell your friends about it, you can send them a link, hopefully, in a couple of days. And then I'd like to thank the student group, Inspire. Inspire is the newest SRO, student something or other organization, student registered organization on campus. They are dedicated to education and outreach related to photovoltaics, solar cells. And they had the little display sitting outside. If you visited their table, you may have had the opportunity to grab half a raffle ticket. And we will be giving away some solar kits, some photovoltaic kits, at the end of today's talk. I'll have, in particular, Julia Hardy who has been incredibly helpful to us, will come up and help draw a few names. And this is the Inspire group. They recently were using one of our labs upstairs to hold a little clinic on building those kits. You can see it's an amazing group of kids dedicated to finding alternative sources of energy, and in particular, harnessing the power of the sun. All right. With that, I would like to introduce today's speaker. Of course, it helps to work out the bugs beforehand, but today's speaker, of course, is Phil Krein, my distinguished colleague, and it's my pleasure to introduce him. Phil, among his many honors, I would say is most significantly a graduate of this department. And so in 1980, Phil graduated with a PhD in electrical and computer engineering from the University of Illinois. Phil is an accomplished researcher and author. He is one of the founders of the International Future Energy Challenge, a major student competition involving fuel cell power conversion and energy efficiency. He is a registered professional engineer, which is no small feat. And Phil, are you the only registered professional engineer right now in my department?
No, I'm not.
Ooh, okay, we'll have to come up with a list. It's an impressive accomplishment, especially for an academic. It means you really do things. And it's a tremendous honor. Phil is also a Fulbright Scholar, a university scholar, a past president of the IEEE Power Electronics Society, an associate editor for a couple of top journals in his field. He's been honored with the IEEE William Newell Award in Power Electronics and is currently the chair of the Transportation Electrification Community. And Phil, for the last 7 years, has also served as the chair of the New Building Committee, which is what you're sitting in the new building right now. And so we as a group are incredibly grateful to Phil for his efforts in bringing us this new space, and we're grateful that he's able to give us the inaugural talk in Saturday Engineering for Everyone. And without further ado, Phil Krein.
All right, good morning. Welcome, everybody. I'm glad to see so many people here. He's taken away my things, but I wanted to tell you what was on those displays. On the left one, we've been taking a snapshot every 15 minutes since January the 1st, 2008 of this particular site. So we have this tremendous time lapse, which probably I'm the only person who's not real bored looking at it. But it's fascinating to watch the holes get dug and all the things moved around, the steel going up and all the rest of it. And we call this our ECE upgrade because it's such a great building. And by the way, on your way out, in addition to some of the other things were mentioned, we have coasters for everybody. So feel free to grab one of those as well. So I will be giving you some insights into kind of what's going on behind that and some of the engineering with it. And one of the things you'll have the opportunity for later is one of my teams of students actually volunteered to make a full-blown, all-up external model of this building sitting right here. So thanks to Tom Navidi, who spearheaded that effort, and it's something you can look around on without having to somehow get on a drone and drag yourself all the way around the building. So there's lots of good opportunities there. And I want to talk about some of the things that came in behind this project, because there are a lot of really unusual things about this building, and we want to touch on some of those. So go ahead and give me the laptop here. Great. So we call this Build It Greener. Some of you have probably seen a show on Discovery Channel called Build It Bigger, right? Okay, we'll talk about bigger here as we go along too. But greener, that's key, right? That's what we really want to accomplish going into the future. And here's a little bit of the motivation, but this is misleading, okay? This is the kind of thing people put in front of Congress, and I've been trained for many, many years as a skeptic, so I know how to read this chart, okay? So it says that in the United States, all of the energy that we end up paying for, 41% of that goes into residential and commercial buildings, okay? That's a lot of stuff. 31% goes into industry. Well, industry works in buildings, okay? So 72% of the energy goes into buildings. Guess what? The other 28 doesn't. It goes to things that move. Now, the thing that's misleading about this is, what if we changed it? Okay, does this mean that all the energy goes to transportation and none of it goes to buildings? That doesn't make any sense, right? In the long run, 200 years from now, I can just about guarantee that roughly 72% of all energy will go to things that don't move, and probably about 28% will go to things that do move, okay? So that's never going to change. What we want to do is make it smaller, right? We want to make the whole circle smaller, but we can't really mess with the fractions. So when people in Congress say, oh, 72% of energy goes to buildings, we have to do something. Well, okay, whatever we do, it'll still be the same number. So we got to go after the right problem. The better measure, for example, is how much energy per square foot, or for example, per square meter, does a building actually use? Okay, this building is spectacular. Okay, at least I think so. The data are still coming in, but it's looking very promising. Well, we think of buildings as things that architects do, and maybe construction companies. You know, what do engineers do in buildings? Well, first of all, engineers are the ones who have to make the choices about everything. And what do I mean by everything? I mean the engineers have to figure out how deep the hole gets dug. The engineers have to figure out whether the dirt will actually hold up the building. The engineers have to figure out how big the steel is going to be. The engineers have to figure out whether we can make that steel vertical enough that it'll stand up when we're done. The engineers have to make sure that when the wind blows, the building doesn't sort of, you know, tilt over, and so on and so on and so on. They have to design it. They have to make sure it works. They have to make sure it'll be safe. Many times we have to test things if we're not quite sure, to make sure they really will work the right way. And on top of this, of course, buildings, there's lots of codes and rules and regulations and safety stuff. That's all great. Now the construction people come and make the building. Okay, the engineers and the architects too are responsible to make sure they do that right. This building is a great case in point. We had a wonderful design, and we said, boy, if they can just build it exactly as intended, it'll be great. Well, you know, 95% of the time that's true. The other 5% we're still working on, but it's okay. It's getting better all the time. We don't need all of that stuff. So here's a few views, a little bit, a few things from the time lapse and from some other angles, giving you some idea from when it was a hole in the ground in roughly February 08. Gee, that's a long time ago. February 12. I'm getting the dates wrong. It's not that long ago. It was still a long time ago, right? February 12, so 3 years ago, it was a hole in the ground, and steel superstructure coming up. And we right now are somewhere above this particular hole in the ground, having this session this morning. Now, one of the things that drives the things we do in low energy buildings is indeed related to students. Many years ago, the Department of Energy, pushed by a lot of people, said we want to have some sustainability goals. We really want to have buildings that use much less energy. And they put together something called the Solar Decathlon Challenge. Some of our students have been involved in this for a long time. There is a U of I team in there somewhere, and if I knew what color shirts the Department of Energy gave them, I'd be able to pick them out. It should have been orange, of course, but it wasn't. You get what you get. But anyway, their job was to figure out how to build houses, and those are sitting on the National Mall in Washington, D.C., that basically produce more energy than they consume. Okay? Now we can do different things with that. We can say, well, great, if I have more energy than I need, I don't need to connect to the power grid at all. Well, that's great if you have a cabin somewhere in the backwoods in Door County or something, but you know, the sun doesn't shine at night. Okay? And I do like my hot water and my heat working at night. That's a good thing. So I kind of like to have things that do connect to the grid. So we'll have to talk about what this whole idea of net zero energy really means. Basically, it means that a given structure over a course of a whole year will produce at least as much energy as it consumes. Now, that means that I've got to have some kind of resource, right? It's not going to do that just sitting there, unless I got a whole cabin full of middle school kids who are willing to go on a treadmill for hours and generate power, right? You do it, right? Absolutely. But you know, it will get old, I'll tell you. Having tried it a little bit, it will get old. There is a house that does that. Okay, that's an example. We'll see some other examples as well. Here is a building that does that. It's one of the first significant buildings in the United States that did it. It's in Oberlin, Ohio. Give you some perspective, right? 13,600 square feet. I know there's at least one residence in Champaign County that's that big. It's bigger than this room, not a lot. So it's not a really big building. And they put it together in 2000. They talked about how wonderful it was and how little energy it used. Took them until 2012 to actually get to net zero energy. And if you look closely, you'll notice that what they had to do was cover the whole thing with solar panels and cover this parking lot with solar panels, and there's a little bit of other stuff in there you can't see. So it gives us some perspective on how these things really work. By the way, this building behind it is just a big house, so it gives you, again, some scale on how big that building is. Not so very big. This one is different, okay? This is a building that we own as taxpayers at the National Renewable Energy Laboratory in Golden, Colorado. The building is right here, 330,000 square feet, so it is somewhat bigger than this building. The first two towers they put up are slightly smaller than this building. The combination is a little bit bigger. And it is zero net energy. Well, because this parking lot's covered with solar, and this parking lot's covered with solar, and this building's covered very densely with solar. Yeah, that's what you have to do to make it work. It's okay, right? It generates more energy than it consumes. Okay, so that building is tremendous in terms of its energy capability. If you're ever out there, go visit it. But this is hard, okay? It's not easy to do this. Why? Okay, first thing everybody wants to know is, well, how much is that going to cost me? I want a low energy building. What are you going to charge me for that? And given that I do that, how much is it going to cost to actually run the thing? You know, is it going to be more expensive to operate because it's got complicated things in it? The biggest problem in the United States is that most large buildings aren't owned by the people who actually use it and live in it. So why should the landlord spend lots of money given this fancy energy building when they're not paying the energy bill? The tenant's paying the energy bill. So, you know, what's in it for me as the building owner? Hey, now in some parts of the country, certain places in California, I can command a premium rent because I've got a low energy building and it works better. That's okay. Illinois, well, not so much, right? And even here, we got lots of houses that are just leased as well. Actually, I'm pretty impressed with these people. They re-sided their house and really fixed it up. So that owner clearly cares. Bigger problem, right? Sometimes the things you need don't exist, you have to invent them. Not everything we invent is a fancy app or some wonderful, complicated computer or something like that. A lot of them are pretty mundane. For example, our contractor said, well, we can't figure out how to make the electrical work in this particular kind of wall. And I said, why don't we just build a box that'll work? Oh, we can do that? Okay. Turned out nobody had done this before. So we have a patent on it. Sounds kind of silly, but it's true. See that thing down in the lower left here? Maybe you noticed that display as you walked in the door here. Turns out those didn't exist either, so we had to invent them. Okay, we didn't invent the software. Somebody has that already, but we invented the way to mount it on the wall, the box to set it up in, the fact that it's real secure. 3 graduate students with a crowbar would probably spend 3 hours trying to rip it off there. They would eventually do it, but it would take a while. And we also had to invent these devices that will convert solar energy, which will be used on the building here pretty soon in the next few weeks as they start installing that. So, you know, if the right answers really aren't there, you invent the right answer. Now, one of the biggest problems is that almost all big buildings are unique projects. They're what engineers call a one-off, meaning I do it one time and then I never do it again. And the real problem is, what can I learn from that? How do I learn something that I can apply to the next project? And unfortunately, some of the building designs are really not for the people who live in them. They're for somebody else. There's a very famous building that obviously was built for the architect. I've been in that building. Most of the people who live and work in that building hate it. The lawyers love it because the lawsuits about the leaks are still going on. Okay? But everybody in Boston knows that building. The publicity value is incredible, right? So the pain to the occupants traded off against the benefits to the owner, it's very weird, okay? It's very weird. Right? This building was built for engineers. This is that same building at the National Renewable Energy Lab, different view. And it is zero net energy, right? Built by and for, really, engineers. The architects got mixed up in there someplace, but the engineers vetoed a lot of the stuff. So there we go. This one's gorgeous. It was certainly built by and for the architect. This is a Frank Lloyd Wright design, if nobody's ever seen it. The engineers hate it. It took so much work to get that thing to hold itself together. And even with what they've done, it still tends to kind of fall apart. The occupants love it. It's a wonderful place. The architects, of course, were very impressed. And everything else, it's won huge numbers of awards, but eventually it will fall down. Okay, we talked about build it bigger. Some of you know what this building is. Anybody know what this building is? That's the Merchandise Mart in Chicago. When it was built in 1930, it was the biggest building in the world. You know what building superseded it? The Pentagon, 13 years later. Okay? It's still a huge building, obviously. It hasn't changed. It was built for the owner, which at the time was Macy's. They wanted to use it as a huge wholesale warehouse. We don't do things quite that way anymore, but boy, it was tremendous for that function, and even today, it's an enormous wholesale shopping mall. It's quite a facility, and they've been trying to figure out how do we rework this building so the energy consumption goes down. Huge building. But has a big boxy building, actually the energy consumption is not that bad. And of course, we have lots of nice buildings here on campus, but any building involves compromises. Right? And certainly if I'm trying to achieve low energy, I'm trying to trade off cost, I'm trying to trade off known technologies and I'm pretty sure are going to work for a long time. I try to trade off other things. For example, this building, one of the requirements for the architect is you shall design a 100-year building. Now to people from Europe that just sounds stupid. But here, what does that mean? It basically means this building has to function without any major renovation or updates for a full century. Other commercial buildings in the United States do not meet that requirement. Nobody would put up a building and not expect to do kind of a significant overhaul every 20 or 30 or 40 years. So, people say, oh, it costs more initially. Well, yeah, but over 100 years, it's going to cost a whole lot less. So, lots of different compromises. Now, this building, for example, right? How long was it before we did a major renovation on it?
1 year.
Well, yeah, I guess a really, really major reconstruction, right, was 60 years, so that's a little better, but it wasn't 100. I think this building will hold up for 100, we'll see, right? The engineering library. One of the things I want to emphasize, though, is that low energy really involves people interaction. And I don't just mean bands of roving people running around turning lights off, although that's a good thing after hours. I also mean how do we behave, how do we live and work? For example, those of you who are college students know about those little dormitory-sized refrigerators. Those things are horrible. They use as much energy as a full-size kitchen refrigerator. Okay? Wow, they're really convenient. Really? So what we had to do in this building is to have a bunch of little kitchenettes where we can have the big refrigerator, right? So we can tell the 30 people who try and walk in the door with the little ones, no. Okay, leave that behind. You're going to use this one instead. And you know what happens, right? They say, well, who's going to clean it and so forth. And then I can ask, well, who was cleaning your little one? Well, nobody. Okay, guess what? All these things are very much linked to scale. It turns out that in a house, you know, you run the numbers and you find out that, yes, indeed, I can put enough solar panels on a house to supply its energy needs, at least on the average. Can't do it at night. Details. You know, that house is covered on the south side with panels. This is another solar decathlon house built by our students. By the way, this is in the parking lot at the iHotel. Has anybody seen it? Go down, look at it, walk around. Very cool. Very cool. But compromises. Really thick walls, so there's not that much space inside, but it's good space. We'll see it later. Special, really low energy appliances. That's nice and fancy. Very simple roof lines, you know, not fancy architecture. In fact, the people who saw it in Washington said, oh, the architecture's horrible. Yeah, but it produces 30% more energy than it uses. Whatever. Compromises, right? So you can't really do this in big buildings. There isn't enough roof space. But you can in these really big flat buildings. So for example, Walmart has been putting solar in a lot of their installations, any place where energy is relatively expensive. Cover the roof with solar. Hey, great thing for them. They're saving money. They're not doing it just to be nice. And some of the other big box stores that we're all used to could do the same thing. This is the convention center in Raleigh, North Carolina, completely covered with solar. Covers most of that building's energy needs. It's not zero net, but it could be someday. Now, you all know this, but when I design a building, right, it depends on where it is. And we live in central Illinois. We have a climate that I like to call all in. When I show this to people in Europe, they're just blown away, okay, because they don't have these extremes. And we have extremes on individual days, right? Right? And we see what it does to pavement, right? It rips the pavement apart. You know, what in the heck is it going to do to a building? So you got to design a building to be safe and effective and all that over this whole thing. And you got to do things like, you know, handle all the rainfall, handle all the snowfall. So if snow falls in the roof, you don't want the roof to collapse. Those are, you know, those are fairly easy ones. Nasty ones are things like this. Okay? You've been here days when it's changed 20 degrees in an hour. Okay? That's what rips the pavement apart, especially when that goes through freezing and back again. Okay? That's horrible. And, right, where does water go? Well, it goes where it wants to. Somebody the other day was visiting here from Purdue and said, well, how come you guys don't have tunnels so you can walk around between the buildings in the winter? And I said, yeah, that's great, but they're wonderful water pipes. You know, when it rains hard, they're not tunnels anymore. We don't like that. We do have some tunnels, but they have to be very carefully planned, very carefully planned. So how do you do this? You know, I can't do it by myself. The architects can't do it by themselves. You've got to have a great big team. I think couple of people in this room are probably in this photograph, but when we started trying to talk about how do we do a low energy building, we got lots of people together and said, you know, everybody take your favorite thing and put it down and let's see what we can take a look at, and then we have to evaluate. See which ideas make sense, right? Because you can't do everything, and some things are in conflict, as we'll see later. Well, and of course, the first question is, how much does it cost? Okay, there's a really, really expensive building right there in Hong Kong. All buildings in Hong Kong are really expensive, by the way. That particular one was designed with lots of compromises for low energy. The coolest thing about it is on the first floor, they have a whole wall, a vegetation wall. And the idea, I don't think it's working quite the way they thought it would. The idea is the guys who work in the restaurant are supposed to come out and clip off herbs and then go and put them in a salad and stuff. What really happens is that the mister that keeps it watered gets water all over the people who are trying to sit at the tables below it, right? So they're trying to figure out how to do that and not have it raining all over the customers. Details. So how much does it cost up front? But that doesn't, that's part of it, right? How much will it save over the life? If I put in more money to get the energy lower, will that save me money in the long run? And how do I put those things together, right? So for example, in this building, we did everything on a 25-year scale, not a 100-year scale. We're not quite that good at it. But we tried to say, how does this work over a long period of time so you can figure out what you're willing to pay for or not. Now, engineers, of course, what they're used to, right? The design engineering team should know everything about everything in this building. But in addition, they use physical and computer models to try and predict things, to understand things, and to better evaluate what's going to happen. For example, there's something called the Energy Plus model that the National Renewable Energy Lab has available. Very comprehensive. It does things, for example, like try to figure out the energy use over a course of a day by counting how many times doors and windows will open or shut. And where is the sun, and how sunny is this climate? How much heat is coming in on the roof because of the sun? And what kinds of things happen in this building? What are the sort of typical energy uses we might expect? And as you can imagine, that can get really, really complicated. And frankly, not terribly accurate, right? Because every building's different. So it's very hard to make that work. And we end up with some physical models too, and things like the one over here, trying to understand better what's going to happen. Now, for example, our engineering architect firm said, well, we don't think you're going to get that close to your zero net energy result because we think your energy usage is going to be this. I'll put up numbers later. And I said, well, I have my own models. I'm sneakier than they are. And my models are simpler than theirs. And I said, no, we're okay. It's good. Just go with it. Okay? So far, my models are working. Their models are not. So let's see if that holds up in another 3 months. Typically, that works great for a few weeks, but whatever. In fact, some of the kinds of things we use to build these things, what do people do in a building? What do they use energy for? Okay? I don't know whether you can tell all the colors, right? The big thing is heating. Okay? The next biggest thing is cooling. Well, we do them both at the same time sometimes, at least on the same day. Ventilation, very important. Takes a lot of energy. You have to turn over the air in the building or it gets really uncomfortable. Let's see, the next one, there's a little sliver there for water heat, and the next one is lighting. So the big ones are heating, ventilation, cooling, air conditioning, lighting. Okay? And the other things fall off from there. There's another relatively big one in there that's computers. Okay? Now, and by the way, I tried to scale these. So an educational type building typically uses less energy than an office building for the same size. So, heating, ventilation, air conditioning, and lighting dominate, but office equipment's catching up. Computers are catching up. They use a fair amount of energy. The biggest problem that we have in a building is it doesn't matter. Okay? The other thing I had on the other screen this morning when you came in is an image from an infrared camera. We use that in the lab to see things that are hot or not. Okay? When you walk around an office, what do you find? Well, here's a copier. Okay? That uses as much energy over the course of a day as an oven. It does. Okay? And I had somebody complaining, somebody wants to bring a toaster into this kitchen. That's a horrible energy hog. Well, how many minutes a day is it used? Well, I don't know, 10, 15. Okay, the fax machine sitting next to it, which isn't using as much energy, is on all the time. Okay, guess which one is generating more heat? It's not the toaster. Okay, so yeah, the 200-watt computer on my desk is having more energy impact really than a 200-watt electric frying pan sitting on my desk because it's on all the time. Okay, and from the builder's perspective, it doesn't matter, it's all heat. And I got to either pump it out in the summer or maybe in the winter I can take advantage of it not run the other heating so much, right? So it's weird, right? In the end, everything's a heater. And one of the things that means, right, we spend lots of energy, lots of money in the winter heating up the air to come into this building. Lots of money, lots of energy in the summer cooling off the air that comes in this building. But you also have to refresh the air constantly, okay? You don't want to keep that cycle going. It'll just blow you away, right? So the incoming nice fresh air has got to exchange heat with whatever's going out, okay? So you don't have to fight with that all the time. So we have these huge things called energy recovery wheels. There's a bunch of them right below us. There's a whole bunch of them up on the top tower. The fresh air comes in, the stale air goes out, they cross over each other without mixing, and they're supposed to. The theory is that they exchange energy and it saves a lot. That's a huge benefit, but it's complicated. Okay, this was more fun. Solar, right? Everybody says we want to use solar. Hopefully you can tell from this map. Anybody know what's the country in the world that has the most solar? Germany. Germany is a horrible place to do solar energy. It's worse than Alaska. It's the last place you would want to do solar. Not quite. There's worse in Europe. Okay? In fact, if I look in the mainland United States, I see only two places that are even close to this. One of them is up here. That's not Seattle. It's the Olympic Peninsula. I've been up there enough that you can stand in Seattle, and maybe 4 days a year you can see out in the mountains in the Olympic Peninsula, right? The other one, right here, that's Cleveland. I'm from Cleveland. So I know what that, right? We didn't have any sun for 3 weeks in December, right? Took me 2 weeks to notice because I'm from Cleveland. You know, even here, right? Central Illinois, it's not close. It's not close. There's plenty of solar energy around. All we have to do is gather it up. So this is actually good news, right? There's a lot of solar resources in the United States that we should take advantage of. Wind, okay? Oh boy, okay, wind, right? High plains, northern plains, central plains, all the way down to West Texas, lots of wind. Of course, nobody lives here. I know that's an exaggeration, but nobody lives there. Hey, there's a little spot here, right? We all know that, right? You drive north on 57 or 39, there's wind turbines everywhere, right? Well, they're in that spot, okay? By the way, they're also in this spot in Indiana if you drive over there generically a little bit northwest of Lafayette, places like that. So that's very nice, but you know, where do the people live? The people live in places like Chicago, New York, Boston. So, you know, if I want to generate this energy, I got to get from here to here. That's expensive. And people don't like these big wires going through their backyard. Well, you know, we could get off the coast. Okay? Ask anybody you know who's spending time in Martha's Vineyard about that. I'm not going to talk about it. Okay? So wind is actually very hard to get to. So now we got to decide, right? We've looked at these alternatives. What do I put in the building? What do I leave out? How do I decide? Okay? First thing is I got to figure out what the limits are. What can I get away with? What are people willing to consider? What are they willing to invest in? What are the trade-offs? Then I want to use my models to see how close I can get in. How much will this cost? And how much will it benefit me over, you know, 25 years, 100 years, hour and a half, whatever, right? How do I figure out all that stuff and get that into place? So we had to do this actually literally with hundreds of different things. Okay, and we went through sort of that first step, qualitatively. Does this even make sense? Can we make this work? What are the pros, what are the cons? Okay, I'm not going to read this off for you, okay? I'm going to go through one in a minute here. So lots and lots of different things. These are just a few examples. And let me do a couple specifically, okay? So one of them is our cooling system. We use what's called a chilled beam. You can't see it in here. You can out in this hallway. Basically, it sort of looks like a light up in the ceiling, but it's not. what we do to cool the building is we pump cold water through in the summer. It's much more efficient to pump water than to pump air. So instead of cooling air and pumping cold air around, we pump cold water around. Saves a lot of energy. It actually works pretty well. There is a risk. It's a big one. Okay? If somehow somebody leaves windows and doors open and the humidity goes up too much, those things will rain. Okay? They'll condense water. It's great in a lab, let me tell you. We don't have that much insurance. So, for example, it meant that if we did that, nobody can open the windows. We have to have fixed windows. That's a bit of a painful trade-off, but we had to look at that. What's going to give us the best result? I'll talk about this a little bit because some people, I think, have these, what's called ground source heat pumps. Basically, with this, you're taking advantage of the fact that here, the earth down about 20 feet is at a constant temperature, roughly 50 degrees Fahrenheit. Okay? And in the summer, you can pump water down, cool it with that, pump it back up, use it to cool your house. And in the winter, it's effectively a source of heat. It's not a dramatic source of heat, but it helps. Saves a lot of money, but you need a lot of pipes, right? Either horizontally, great big pipe field, or vertically. You can drill down a whole lot as well. So, lots of trade-offs. We didn't do that in this building because the campus already has this tremendous cold water loop all the way around, and it amounts to the same thing. It's at a constant 55 degrees, so hey, that's good. Solid state lights, these are so cool, right? The lights you're seeing here are fluorescent. They're high-grade fluorescent. The lights up here in the front that are off are all LED based, right? You've seen these in the stores. I got two of them, I'm going to pass them around, okay? And if you want to, it's okay. You can take the cover off. And you see these little LEDs in there and a lot of electronics to make them work, okay? Much more efficient, much more efficient. More expensive too. Let's see if this one comes off. Oh, yeah, you can work on it. Don't worry about breaking it, it's okay. The biggest problem with this is when we designed this building, these products weren't ready. They weren't ready. They said, well, you can try this, but they don't exist. Well, we had faith. We're engineers. In fact, the inventor of the visible LED is one of our faculty members, so we said, you know what, we got to have LEDs, doesn't matter, and they'll be ready. Okay? They were, so it's good. It's all good. Building's full of LED lighting, except in places where it's not. Okay, wind. Everybody asks, what about wind on this building, right? We're in a good location. It's not that bad anyway. Architects showed us these gorgeous, beautiful artistic renderings of these wonderful looking things that could go on the building. Wow, that's really nice. And I said, wait a minute. Remember, I'm a skeptic, right? So I said, wait a minute. I want a photograph. I don't want this artist drawing. I want a photograph. There's the photograph. And everybody looked at that and said, no, we don't want that on our building. No, 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 no. Okay. And to put that in real perspective, we also did the structural analysis. How much extra steel do you have to hold that up and to keep it from making the whole building shake? Okay? And after we did that math, no. So there's no wind on this building. Someday we will have wind probably on the parking garage across the way, where it doesn't matter, but not here. Okay, I don't want to run you through this. Maybe I should have left it out. Anyway, lots of things were considered, right? Many were considered, few were chosen. The things in orange are kind of the things we ended up with for many different reasons, but everything had to go through these hurdles. And some of them were eliminated because they were too expensive. Some of them were not. Lots of trade-offs, lots and lots of trade-offs. And this is one page out of about 15 to give you some perspective. That's what engineers do. They compare alternatives. And for example, we looked at things that were in conflict. I already mentioned the chill beams and openable windows are in conflict. You can save energy if you have windows that open. A little bit in Illinois. You can save a lot of energy if you have chill beams. So, even the skeptics said, well, okay, we go with the one on the left, oh well. Overall, then, you end up comparing to these sort of industry baselines. You know, everybody, I mean, it's really easy to go in a room and say, oh, I'm going to use 20% less, 30% less. Less than what? It's just like going in the store where they say, oh, this is 30% off. 30% off of what? Okay? I guarantee it isn't off the price it had yesterday. Okay? We all know this, right? So, compared to what? There is an agreed upon baseline that says, here's what we use for comparison. And we set that up, and we run all the numbers, and if you add those up really quickly, they do add up to more than 100%, as they would have to get to zero net energy, right? Got to get to 100%. However, the big number there, the 55%, is all linked to solar. This is the solar installation on my house, by the way. Really cool. Everybody should do this. Okay? These are self-contained. They've got those little inverter boxes I showed you before. Basically, you put them up on the roof, you plug them in, it's done. Okay? And there are, what, Scott, 2 or 3 contractors in town who know what that means. So eventually, we'll have people who know how to install these. But it's very cool. Very cool, very easy. Cheaper than utility electricity, by the way, if you do it in a certain way. And of course, rooftops are great places to put solar power, right? What the heck else are you going to do on the roof, right? In fact, you also capture sunlight that otherwise would just make the building hotter. So in the summer, boy, solar is great. It does 2 things. It gathers energy and it shades the building. Now, I showed you that one house from the other side with the solar panels. Here it is from the north view, again, down by the I Hotel. So, yeah, building a house that's zero net is physically possible, and it's got lots of nice, cool stuff on the interior. I don't know if you can tell from that image how thick the walls are. Okay, they're really thick, so it's got special windows for all that. The bathroom is very weird. The shower is kind of right in the middle, and the theory is that the water just runs down through the floor and drains away. It's kind of a pain to clean up when you're done, though. But that living room is really nice. So it's a cool place, okay? Here's that building in Colorado again, zero net energy, right? And, you know, again, it's more for engineers, so there's lots of cubicles in it and stuff. But it's got some interesting features. For example, the glass in that building automatically changes color. So that when the sun is going against the windows turn dark. And the question that you always ask, well, how long will that hold up? That stuff typically wears out. And they said, well, they claim it's going to last for 30 years. Okay. This building's got to last 100, so we can't do that. Oh, well. It achieved something that's called a LEED Platinum certification. What that means is leadership in environment and energy design, something like that. The highest level is Platinum. There's a building on campus called the Business Instructional Facility that's Platinum. Obviously, we're engineers. We're not going to let business people do better. But you can't do better than the best, so we have to go to zero net energy. That was our only choice. So we're pushing for that. But for example, what does that mean? It's not just energy. It's also, what did you build the building with? Is it recycled stuff? Did you generate very low waste when you put the building together? One of the things that fascinates me is, you know, this building has a little bit of a new building smell, but you don't really smell paint and stuff like that. It's amazing. The new paints, you know, almost no volatile content at all. Much safer, dry faster, work better, horribly expensive. Whatever. Lots of water systems, water management is part of it, daylight management, all sorts of other things. Now, let me talk a little bit about our building as well. Again, there it is, as a hole in the ground. Like I say, the engineers had to figure out how deep do we build it, what soil conditions are required so we can lay down the concrete and build on it. There were, in fact, 2 places, you can kind of see them. Here's some places where they're building footers for columns. Okay, they found 2 places down in the basement where basically that was quicksand. Yeah. So they had to dig all that stuff out and refill it with gravel and so forth. You know, there's little stream beds under the ground around here all over the place, right? So yeah, you got to deal with that. It's not a good idea to build on quicksand. We started again in January 2012 with the construction, not 08. I keep messing it up. And we did open for the fall semester. This is about center field on the old baseball field. And even before that, Brad, you were trying to figure that out. Is this about the 30-yard line on the original football field? So, well, of course, it's 30 yards wide, so it doesn't matter, right? I can say that and still be right. So anyway, there was a time when Red Grange was running through here carrying footballs, right? Okay, why? This is just very quickly. Our department is actually one of the largest academic departments in the United States. More than 2,000 undergraduate students, more than 500 grad students, about 100 faculty. Okay, whatever those numbers mean to you, this department has a wonderful sense of community and collaboration. We all know each other and interact with each other, and we can do lots more things because of our size than almost anybody else. So it's very good. We gave the architects 3 objectives. One is to provide a home for our students mainly, but for the rest of us as well. 2 is not to duplicate a lot of the stuff in the other buildings nearby. And 3, we challenged them to create the most energy efficient engineering building in the world. And in the end, they said, well, maybe we can go all the way to zero net. Okay, let's do that. We're still working on it, right? But it'll happen. Lots of different things in this building. You're in the auditorium, right? But there's offices, there's teaching labs, there's research facilities, lots of classrooms. Everything you can imagine is in this building, I suppose, including the clean room is out here. And we've seen a couple of views, but there you see it a little bit farther after the walls began to go up. And then even as the facade goes up, and here you can start to see the insulation material and how the wall system works. I'm not going to give you too much detail there. And that's a photo from December. And this is the artist's rendering from about 2011. It's pretty good. It's pretty good. It's good enough that I do think I like that one better. Okay? Very cool. So they, you know, again, they designed and built what they said they would. That's great. The top is a rendering of the clean room. The bottom is a photograph of the clean room out here. Okay? So again, came out pretty well. There are about 24 different teaching labs in this building. Huge number. Lots of places for students. Okay, size. This building is about 236,000 square feet. Remember that great big one in Colorado was 330,000. Okay, it's bigger. Not hugely, but it's bigger. The cost of the total budget was $95 million. Half of that came directly from the state as capital project support. I won't make snide remarks about Champaign Unit 4 and that number. Anyway, the construction bid was $71 million, which is right at $300 a square foot, which as an engineer makes you wonder about the construction people, because somebody knew how to divide, that's good. Whatever. Anyway, that was considered good, you know, that's for a 100-year building with all these features, that's actually pretty good. Try to do a nice fancy building in downtown Chicago for $300 a square foot, good luck with that. That previous slide had a rendering of the auditorium. This one's a photograph. I like this room. Even though I'm shouting, I know I don't need to, whatever. And there's the lab across the way. This is the freshman lab, one of the busiest places in our department. There are lots of little robot projects and other things that go on in there. Great facility, really wonderful. So we have kind of this tower system that we're right here, sort of in this south tower down in here. There's this set of north towers with the labs and with the offices basically here. And by the way, when we're done here, if you want to take a little bit of time and wander around, if anybody questions you, you can just tell them I said you could. It's all right. Not a problem. The building is supposed to be public and open, right? We don't need all the layout, but here we are, right? So a few photos showing how it came together. For example, everybody says, oh, my cell phones don't work in this building. We heard one go off, that's good. But most of them don't work, right? Because everything's made of metal. All the floors are made of steel, all the walls are made of steel, even the windows, because they're special glass, have a metal coating. So in my office, my cell phone just dies. It doesn't work at all, okay? Down here, it's not as bad because there's more glass, but you get the idea. And a few more interior views. For example, this one shows how the ventilation comes in above those chilled beams to change air in the building, and then how some of the office areas are set up. You may not get to walk through upstairs, so that gives you some of that. This is one of my favorites. This is where we're sitting right now. Oh, wait a minute, I got to get in the right position, right? Right about there, okay? So here we are in the auditorium, right, laying that up. If you were to look carefully, and you might look under your seat, there is a vent under every single seat in this auditorium, okay? What that means is that right now the ventilation system is going full tilt. Yeah, that's pretty good, huh? Okay, very low energy, very efficient, very effective in keeping the air fresh, and no noise. In fact, I could talk like this, and I'm sure I can get away with it. But I like to talk louder, so it's okay. Too many kids, right? I have too many kids. How do we do the low energy? The walls are certainly part of it. The numbers, maybe they mean something to you, maybe not, but the walls in this building achieve R30, which is actually pretty good. There's a lot of passive solar design around to shade the building during the summertime and so on. Solid state lighting we talked about, but it's in 80% of the spaces, okay? And the rest of it is high-grade fluorescent. The heating, ventilation, air conditioning I talked about. Here's a chilled beam. Here's the ventilation system interacting with it. And here are these exchange wheels. And then our heating system actually uses this weird chiller stuff. I won't mess with that. And we're getting ready now to install the solar on the roof, because we got to have solar to get to zero net. Okay, our roof will hold about 300 kilowatts peak. That's roughly enough power to supply about 40 different houses. And then we're going to put more on the garage that's over here. And between those two, we should be good to go and hold ourselves up on the average over the year. So we have a building now that can be a living lab and can help all of us figure out ways to do things in many different kinds of buildings, certainly this one, and other office buildings, other campus buildings, and so on. And again, the photograph and the rendering, okay? I got to get out there in the evening and get it with the lights on, right, so I can match it up. But we're very happy with this result. I have this wonderful model here, and I would love to take your questions, right? I didn't emphasize this. The design engineering team, okay, is supposed to be able to justify and explain to you every single part in this building. Okay, if I ask the guy, why is there a bolt over there, he should be able to tell me. Okay, now I can't, no one person can do that for every part of this building, right? And I'm part of what's called the user team, so I'll try my best. But thank you very much.
Can we do a couple of questions, and then I'll get Julia to do the raffle, and then we'll take some more.
Whatever you want to do, yeah.
Okay,
so a couple of questions, and then we got a raffle. You can ask anything, yeah.
You mentioned buildings that can produce more energy than they use ultimately. So if that went on for a long period of time, could that ever become a problem?
Okay, so the question was, some buildings in principle, like that house down there, can generate more energy than they actually use. If that became a real big trend, how would we deal with that? How would we manage it? And in fact, that's a really important area of research right now, is how do you get enough control so that these things look like sort of conventional power plants? You can't make the electricity grid just be a backup. That's nonsense. The nuclear plant in Clinton, Illinois was not designed to be a backup power plant. Okay? It can't be, it never will be. Worst case is we tell people to turn off if there's too much there, right? That's fine. Better case is you go get yourself a nice plug-in hybrid car, right? And charge it up with whatever you have as your excess energy and go up to Door County and visit your neighbor's off-grid house, right? All right, other questions?
Well, on line to that question, isn't it also possible that you could sell the excess energy back to the company?
Well, right now, okay, so kind of a little bit beyond that. Illinois does what's called net metering, meaning that when I bought those solar panels and put them on my house, it just basically comes off the top. Okay, it's just taken right off of my meter. And if it goes all the way to zero, they give you some credit, right? Scott's house has many more panels than mine does, so he actually goes below zero. But your bill never goes below zero, but they give you credit for the whole year, right? They'll never send you a check.
Well, I have 2 electric cars now.
Yeah. So he's driving for free, he's living in his house for free, and the utility company's still pretty happy. We'll take one more, then we'll give it to these guys. Yeah.
So in Illinois, like what percentage of the power that you get from the power companies is renewable, and do you count that towards this building?
Yeah, in Illinois, there is a mandate to have more renewable energy into the system. I think we're shooting for 20% by 2030, something like that. In this building, we're not including that. The campus as a whole, of course, is. But we think that our local solar resources will be enough to do the job. It'll be close, but they might be enough. I see a couple more questions, but let's go to the raffle, and then we'll have plenty of time for more.
Yeah, so we realize people may have to go, and so I'd like to invite Julia up. Julia, and if you would, I'll hold the bowl, and if you would call out the numbers. Julia's going to give away 3 little solar charger kits that Inspire put together for us.
Oh,
Yeah.
she's got a mic. Yeah.
Yeah, I have a mic. So the first one is 521143. So if anyone has that ticket, you guys can come up and grab a solar charger.
Do I see a hand?
521 143.
All right.
Yay.
Let's roll through these. I think people have to go.
Okay, second one.
The next one is 521136.
Right over here.
Awesome. And the last one is 521145.
Are you still here?
Yeah.
Oh,
in
hey,
the
we've
back.
got one
Okay.
back there.
Awesome. Thank you guys so much for coming out.
Okay.
Thank you, Julia and Inspire. We really appreciate you being here today. I think what we'll do is we can take a few more questions.
Let's
If you
do it.
have to go, of course. There's a fine line between a public lecture and a hostage situation. We'd love to have you do some more questions. If you'd like to wander around the building, please do so. Please feel free to grab some snacks on your way out. Thanks.
Okay, I saw another question in the back. Yeah.
I'm just curious, what level of detail you're trying to design, how efficient things are. I was just looking at the exit sign, for instance, and saying, somebody actually look at that, because things have to be by code, obviously, and, looking at the carpet, is there any significance to the carpet? Is there any significance to those speakers we have up there? What level do you get, of detail to try to make it incredibly efficient?
Yes, so his question for those, I'm sure most of you didn't hear it, is how much detail do we need for usage? Okay, how do we really tell how much energy is being used in the building? And the answer is as much as we can possibly get, but a better answer is to try and get perspective, okay? Every individual person in this room is a heat load somewhere between 60 and 100 watts, okay? That exit sign, we did look it up. It's about 7 watts, if I remember right. Okay, so yes, we have this huge spreadsheet with all this stuff on it, but the fact that we're all sitting here right now blows away everything else in this room. And that's true when the building's occupied, right? It's not true at night. It's not true on the weekends. So yes, we have this huge spreadsheet and we try to put things together. But yeah, there are some things that they're kind of too low to make a big difference, and you have to put in either a guesstimate or a rule of thumb, or you just say, well, it's not going to make that much difference.
Just a follow-up on that then, does that mean if we were all a lot lighter, we would have a large impact over the year on this facility or not?
It is definitely true that if this were an elementary school, you would consider the effects of the people load, quote unquote, differently than you would in this college facility. Yes. We don't have that problem here, of course. This is a great place where kids can be during this kind of event, but it's not that common, right? But yes, absolutely. You have to know the use case of a building to really do the job properly. The trouble is, it's still not an exact science. We haven't been able to get close enough, so that's why the architect says, no, you're going to use 2.5 times as much energy as I think we are, right? The reason is not that I have better models. I don't. The reason is I understand a little bit better how the building is used than they do. They don't live here. Yeah.
Are your chilled beams fire protected?
Well, there's no chilled beams in this particular room because it's not. It's too big for that. But the chill beams, because they're just water pipes, you know, there is fire protection in all the structural elements. You don't actually have to do that in the chilled beams. There's a separate sprinkler system, so it's not integrated with those. But beautiful thing about chilled beams is since it's all water, right, it doesn't add any hazards. Yes, in the back.
So is this an interesting one-off? Like, what do the things you learn from this change the way the UI is going to build buildings in the future? Presumably not all their buildings in the future are going to be net zero, but what are they in general?
Well, that's a really good question. So how does this, as a one-off building, like so many others, help influence practice on this campus and elsewhere? There's actually two major things. For example, when we put this design together, the campus had said our minimum target is LEED Silver. As we put this together and they looked at, you know, it doesn't cost that much extra. They said, okay, we're going to go to LEED Gold. I think in another 2 years they're going to say, well, heck, LEED Platinum. Okay? So yes, it shows them what we can afford to aspire to. So that's a major thing. Number two, okay, this is an issue, right? Oberlin is an example. If you can do a big zero net energy building in Urbana, Illinois, you can do it almost any place in the United States. When you start looking through energy use requirements, not just weather data, okay? The toughest places in the U.S., number one is Minneapolis. Number two is Chicago, okay? And we're not a whole lot far behind that. So if we can do it here, people can use these kinds of ideas almost anywhere. Absolutely. So yes, it's making a difference. And the campus is indeed toying with, you know, how should we do things differently in the future? Yeah.
Along the same lines, is there anybody tracking the efficiency of all of these separate, another one-off buildings, saying this one is working particularly well and it's because of the chilled beams, or and then taking all of that and making new standards for platinum or the levels?
Yeah, that's a great question. Are people tracking and trying to gather the data from these things? That's emerging. The LEED people do update their standards basically almost every year. So they're trying to get some of that. Right now, there isn't a systematic database that's trying to record these. Everybody sort of has their own way of doing it, and there are a lot of reasons for that. One of the things that we're trying to do as a future project is exactly that. How do we standardize data reporting? How do we make sure we're getting measurements down at a low level so we know what's going on? And how can we report that in a way that can influence the way people use things? So that's a big part of what we aspire to in the future, yes. Yeah. How are the solar panels protected from the weather? It's actually interesting, and the model, even though it's a little bit funky on the solar panels, gives some example. Solar panels themselves, they're semiconductor cells, they put glass in the front of them to protect them from, you know, dirt, debris, and rain. And then the rest of it is about just making sure it's attached well enough to the building so it doesn't blow away. And beyond that, you know, it's not that we hope for the best, it's that we, you know, for example, the people who make solar panels test them by firing hail at them and say, you know, can it handle this without breaking? We do calculations to say, okay, can I put a foot of snow on this panel and it won't bend and break? You know, is that weight okay? So we do all that stuff too. In the end, you can't be perfect. One of my friends had a solar installation, and one day we went to his house and we looked up and we said, you know, you got a little circle on your solar panel. Looks suspiciously about the size of a golf ball. He lived next to a golf course. Somebody missed, or maybe not. Yes? Yeah. Right, right. Well, okay, so the question is really sort of what do we mean by a 100-year building? And it's not defined that well. We tried really hard to design this building so it doesn't need remodeling and a lot of significant structural work over that kind of time frame. You know, obviously if an accident happens and somebody breaks a window, that's a different thing. But these windows, for example, all the material that was used to seal them up is supposed to last for a long, long, long time. You know, they didn't go to Menards and get the 5-year stuff off the shelf. They had to go to the manufacturer and say, you got to sell me 50 or 100-year sealant material and so forth. So it was a lot of attention to what went in to make sure that things won't wear out. And a lot of effort on the design. Do we have enough flexibility that we can do what we think we need to do? I mean, you know, we don't know what we're going to be doing in 50 years without having to totally redo the building. I think it's safe that we'll need this auditorium for a long time, so that helps. Yes?
Just a question about those little solar kits that you take out. Do you make those, or can you buy them somewhere?
Hi, I can answer
Here.
that one.
Here.
Those,
Do with this.
thank you. Those were actually built by our students upstairs a couple of nights ago. And if you stop at their table on the way out, they can tell you more about it and how you can get them yourself and how hard they are to make, which is not too bad, actually. So, actually, could I suggest that we're kind of getting down to a small enough group that I would invite everyone to hang around, come up and
Walk
talk
around
to
the model.
Phil, come look at the model.
We'll
There's
maybe
probably some
muck around
bagels
with the IR camera a little bit.
Yeah, look at the IR camera, and we will hang around, but
somebody
I
said
don't
that.
want people to feel stuck. And we really appreciate everyone coming out tonight. It's wonderful to share a new building with you, and thanks for showing up today, and we hope to see you again in 2 weeks. I'll be talking about medical imaging. And so with that,
Great.
thank you very much, and let's thank Phil again.
Illinois.